And so, what I wanted to show today was just how interesting certain like toy models in physics. So, because this is something that when I was learning, I thought there was almost no use for these models, and after you start building up more knowledge, you realize that there's actually use for them. So the toy model that I'm going to be referring to is the infinite square well. So for those who don't know, the infinite square well model, it has a zero potential inside of this box, and this box is of length a, and the potential outside of this box is infinite. And what that basically forces it to do is a particle cannot escape from out of here, right? And this is a completely solvable model. So when you solve for the Hamiltonian of a system, right? Basically, the only thing you're really solving for is the momentum squared over 2m of your wave function. And in quantum mechanics, that leads to negative h bar del square 2m. And so the solution for this system sets ends up giving you signs. And what you end up finding out is that the energy is equal to something of this form. It's h bar squared, pi squared, n squared, where n is the energy level, over 2m a squared, right? And so you'll have energy levels, for n equals 1, n equals 2, n equals 3, and so on. And so the neat part where we ended up using this toy model is we ended up looking like to recognize that this energy is actually dependent on the size of this model, right? And so if you actually have some atoms, right? You have them split apart. And let's just say hypothetically that you have electrons in here and they're isolated in an area A, right? Then we could approximate this to be some form of an infinite square well. This electron doesn't want to be away from this electron. And we know this is a bad approximation, but it's still an approximation, right? We could approximate it to be this, right? A. So they're all A, right? And in metals, we know that when you put them all together, the metals kind of all share their electron spacing. So rather than looking like this is all trapped in region A, now the electrons are trapped in a larger region. We'll just say big A for now. And so one thing that we want to think about is when it comes to bonding, why would a single, let's just say, metal atom want to combine to make a metal solid, right? Well, a lot of times things want to take the form of lower energy. And so, how can we compare these metal atoms to a metal solid? And we're going to assume this toy model system. So, if we assume that each of these metal atoms is like a toy model, then this thing's like an infinite square well. At the ground state, it'll take on each, this basically constant, right? So for each of these, we'll say E1. It's just a big constant. We'll say C is equal to all this other stuff, to C over A squared, right? We'll say this is E1, E1, E2, and so on, right? constant over a squared, constant 3 over a squared. And if we had, just say, 6 more, it'd be the same thing. And so now, if we were to compare these electrons in here, right? Let's just say there's 6 electrons here. But for one electron, now this one electron has the same constant. Rather than a squared, it's going to be big A squared, right? Let's assume big A squared is just, it's the same as this. That let's just say it's 3 times the size of one of these. And so if we say it's 3 times the size, what this thing would do is actually say 3a squared. And this is 9a squared. Hold up, let me check something real quick. Oh, yep. I just want to make sure this is still running. Okay. And so if we look just for one electron in this system, the energy actually dropped by a ninth, right? This is literally 1/9 of the energy here. And so we can say that this electron, all the way down here is also a ninth of this. And so the total energy of this system, it's E1, and you add up all the way to E6, it's going to be 6 times C over 2A. And if we add them all up to here, assuming there's no interaction term, it's going to end up being the same thing, 6C over 9A squared. And so there's, you can see that this is 1/9 less. And yes, we're not considering electron repulsion, but then that would just add up another little factor, which we could then approximate as well. And so that's something else we could approximate. But I just thought this neat little toy physics model kind of explains some of this phenomenon pretty well, um, such that you end up seeing that having a metal solid where the electrons kind of share the space is actually lower energy than just having a single electron in a single atom. And so we could see that the energy is lower in this metal solid case than the metal atom. And this doesn't account for other covalent bonding and other systems, but I just thought this was a neat little toy model that I thought I learned a lot about and I thought I'd share. And so if you have any questions, feel free to comment, and I'll just keep sharing neat things that I keep learning. And so for now, I'll say thanks for joining, and I hope to see you next time. Bye bye.